we are going from N1 to N2. Transition term is this. So in this transition terms, R here is my Rydberg constants. Okay, R value is a Rydberg constant is this. Now this Rydberg constants, it's a value you can remember here, but it is going to be something around your, nearly around your 91.2 nanometers. So 191.2 nanometer inversely in terms of distance, if you remember, right? So if you remember here R as a 1 by 91.2, in problem solving it is easy. It also going to be have a relation, this 13.6 electron volts is equals to RHC. So these are another useful relations in problems. It is much helpful. So anything related to the wavelength, you can use here the R as a 1 by 91.2 nanometers, right? And in this case here, different transition terms are there, Balmer, Lemon, Balmer, Pastures, right? So all these series are there. So if you have, this is a point you remember, everything else you can derive very easily. Okay, so just remember this point. No need to remember all the formulas, not required at all. If you remember, it's well and good. That's good. But if you remember this 3-4 points, it's going to be enough to solve maximum problems. So what is my radius? The radius here is proportional to n square by z and inversely proportional to mass terms. Proportionality constant is 0.51 angstroms. Velocity is proportional to z, inversely proportional to n. And proportionality constant here is our C by 137. Okay? Energy is minus 13.6 z square by n squares. Now energy is half mv squares. So v is a z by n. So my energy is a z square by n squares, obviously, right? And the wavelength, you can find out the wavelength from the energy. We have yesterday proved it here. But if you remember this Rydberg constant relation, it is also useful. Now suppose I ask you one question. Suppose that there is a lithium ion. Okay, lithium ion atom is this, and the electron revolves. Electron is going to be revolved in the third excited state. Okay, third excited state. Electron revolve in the third excited state. So can you tell me, find first thing its accelerations, find its accelerations, okay, find its kinetic energy. Many things they can ask you. Time period. Okay, they can ask you here current, because electron revolve in a circle, so it executes current. So current, what is the current? As a magnetic field, it will create. So many things could be asked here, but all could be done quite easily. So there is no need to remember the formula for the frequency. Okay, you can also write down here. This is a time period and frequency. Na? So time period and frequency. This is time period. Find out the time period of revolutions, accelerations, kinetic energy, current, magnetic field. Okay, I'm just telling you, don't remember many formulas. It is going to be confuse you. Just remember the proportionality, and from this proportionality, we can find out everything, and quickly. We can find out quickly, not slowly. But the first one is accelerations. So what is my accelerations? In circle, my acceleration is v square by r, right? Acceleration here is v square by r. So if I'm going to write here, my velocity is z by n. Okay? Proportionality constant is your alpha. Alpha value is 2 into 10 raised to the power 6. R value is proportional to n square by z. Proportionality constant is a 0.51 angstroms. If I think about here, my constant proportionality, if I just write here first proportionality. So what is my proportionality? Proportionality here is z by n square, and the radius proportional is n square by z. So I can say my acceleration is proportional to z cube by n power 4. Okay, that's my proportional. Now there are two ways you can find out the accelerations. The first one is expression of the accelerations. Expression of the accelerations. अच्छा इसमें भी और आ जाएगा. If you want here, it is radius is inversely proportional to my mass, and my velocity is independent of the mass. So if you want to find out here these expressions, so three terms are there: charge term, mass term, and angular momentum terms. Okay, so I'm getting here these accelerations. This is my three dependence of the accelerations, right? If you want to find out here the expressions, you can take the mass also terms. If you want to find out the proportionality, mass is not required. Okay, mostly mass is not required, but if you want to find out the exact formula, then the mass is required. So mass dependence is also required. So that gives me the exact expression here. So in the exact expressions, z terms always come with the charge. There is no other way for the z terms. So z term you can replace with the k, z, e squares always. N terms comes because of angular momentum, and the mass term is m. So that is the exact formula for accelerations, right? This is the exact formula for the accelerations. I hope you understand the point here. But if they're asking here value of the acceleration, so how we find out the value of accelerations? The value of accelerations, you can use proportionality. For the value of accelerations, you no need to substitute the mass, k, z, nothing required here. So what you can do use here is, I know my velocity is z by n, and velocity is 2 into 10 raised to the power 6 z by n squares. Radius is 0.51 angstrom, and radius is n squared by z. Okay, so that is my acceleration in terms of value. So in terms of variables, okay, that's my acceleration in terms of variables, and that is my acceleration in terms of value. So both way you can easily find out the accelerations if you know how your velocity and radius depends upon the mass, charge, and angular momentums. Okay, that's why I'm telling you, no need to remember here many formula. Just remember that velocity and radius. And velocity and radius and everything else, it only depends upon three parameters: charge terms, mass terms, and angular momentum terms. There is no fourth terms. Okay, so there is no fourth terms. I hope you understand the point here. Is it okay? Clear? Anyone have a doubt here? Very good. So next he is asked here lithium. Lithium and the third excited states. So what is lithium? Lithium, you know, na? In lithium, you have Z value 2 or 3. So lithiums, in your periodic terms, you should have an idea, but it will give you, it will be given in the questions. Z value is 3 for the lithiums. It's a lithium ions, 2+. Take a single electrons. To apply the Bohr's model, single electron is compulsory. But the next one here is, it is in the state, third excited state. Can I say n value is 3? No. The third excited state here, my n equal to 1 is basically my ground state. Okay? And then you're going to have excited state 1, excited state 2, excited state 3. So basically, third excited state is you jump from the ground. Okay? First, you go here, n equal to 2, n equal to 1, to the n equal to 1 to n equal to 2. That's first excitations. Then you go to n equal to 3. That's my second excitations. Then you go n equal to 4. That's my third excitation state. So here n value is not 3. N value here is 4. Yeah, you can put the value of z value 3, n value 4, and you can find out the accelerations value wise. Okay, I hope is it okay, clear? Sorry, go little slow. So already done, hai na? This is already done. Topic is done. So anywhere you have a confusion, so once again listen here. So what you need to remember is simply you need to remember this two proportionality. And what is keep in the mind is that there is only 3 terms. There is no 4th term is there. Charge terms, mass term, and angular momentum terms. These are 3 variables who define the whole atoms. Okay, so they are complete. If you know about the charge, if you know about the mass, if you know about the angular momentum, you know everything about the atoms. So my velocity depends upon the charge by angular momentums, but it is independent of mass. Radius depends upon the angular momentum square, charge inversely, mass inversely. Okay? Proportionality constant of the velocity is a 2 into 10 raised to the power 6. Proportionality constant for the radius terms, including mass, is a 0.5. That thing only you need to remember. Okay. So next thing you can easily tells me here, kinetic energy and time period. Kinetic energy and time period. If I write here kinetic energy, so total I told you kinetic energy is same as total energy but negative. The total energy is negative, kinetic energy becomes negative of negative positive. Okay, same as total energy. And total energy, how much is that? It is minus 13.6 z square by n squares. Okay. So if you have a confusion, you can remember that it is half mv square, and v is a z by n. Okay, so v is z by n, so it is proportional to z by n. So why n equal to 4? Yeah, third excited stage. The third excited stage. What is excitations? If you make a jump from the ground state, first excited state, n equal to 2, and 122, first excited state. Then you make a jump to 1 to 3, that's my second excited state. Then you make a jump from 1 to 4, that is my third excited state. Is yes, Aditya.
Problems will.
Repeat again.
Problems will.
Problems given up. Sorry.
Sums will do, sir.
You can do the problems. We are discussing the problems only quickly. Okay. So the kinetic and total energy is minus 13.6. Z square by n. Z is 3, n value is 4. Okay. So what is my kinetic energy? So kinetic energy comes out to be your 13.6 positive. Z value is a 3 squares, and n value is of 4 squares. That is my kinetic energy in terms of electron volt, 13.6. But if they ask you about my 13.6, if they ask here the energy in terms of SI units, so electron volt you can convert into a 1.6 10 to the power minus 19. Then it turns out to be your joules energy. So that's the kinetic energy in the joules, right? After kinetic energy, what I asked you at time period. Time period and frequency. Time period and frequency. So we know time period in circles. Time period here is 2 pi r by v. Okay, 2 pi r by v. So r and v, you can substitute the value of r and v. That will give the time period. If you reverse, it will give the value of frequency. R is proportional to the n squared by z, and velocity is z by n. So if I write here r by v, so r by v, my time period is going to be proportional to n cubed by z squares, right? N cubed by z squares. So if I have to write down here my time period formulas, so I can replace 2 pi is 2 pi. I can replace here n. N I can replace here with the, oh, sorry, just a minute. Mass is also there, inversely proportional to the mass terms, also there, and V is independent of the mass. So mass term is also going to be come into the picture. So we have in terms of mass, mass is also required if you want to write the expressions. For this expression purpose, I can say my time period is 2 pi is there, constants, and R and V, R by V ratio. If you want to replace your R by V ratio, so R by V, I can write it here as a NH cross Q. Z we can replace here with the KZE squares and inversely with the mass. Right? That is my exact time period formula. For value purpose, if you want to find out the value, R value is a 0.51 angstroms, and R here is n squared by z terms. Velocity term is 2 into 10 raised to the power 6 and z by n. So I can get here the time period, right? Next, I ask you about the current. Current is charge flow by time taken, and my here charge is E. Electron is revolving. So electron is revolving around the nucleus. So charge flow time taken, that is my current. So exactly same is theirs. Okay? We can substitute here the value of time period, that will give me the current. And for magnetic field, so for magnetic field, this moving electron is going to behave as a current. No? So if there is an electron moving, it's a negative charge, so it is generating a current in the opposite directions. So it behave as a current ring. So electron is behaving as a current ring. For the magnetic field, you can apply the concept of our current ring. So there is a current is there. So magnetic field at the center of the ring. How much is magnetic fields? We have derived the formula for the magnetic fields. That was our mu naught I divided by 2r. It's going to be mu naught I by 2r. So I can write here the magnetic field is mu naught current value here is E by T divided by 2R. Further, you can write it here as a mu naught E by T. T factor here is a 2 pi R by V. Say it. Time factor is, sorry, in the denominators. Time factor we're going to have in the denominator is 2 pi R by V. So overall, it's also depending upon your velocity and radius factors. So V naught by 4 pi E adds V by R square. So V by R square, you can substitute the value of the V, okay? The V value and R value you can substitute here. What is my V value? V value is Z by N. Or exactly, I can say here it is going to be KZE square by NH cross. That is my exact value of the V. R value is N square by Zm. Okay? Or exactly, you can replace the N as NH cross. Z you can replace with the KZE squares and M. So we can put the value of this R and V, and that gives me the magnetic field. So mu naught by 4 pi E value. Velocity term here is KZE square by NH cross, and the radius terms we have is a NH cross. NH cross divided by KZE square M. Right? So slightly, if you rearrange, it will be mu naught by 4 pi E. I'm going to be have a Z term is going to be a cube term is this. In the denominator, you have a square terms. Z term is going to be my square terms. And NH cross is going to be my cube terms. And one mass term is there in the numerators. Take it down. Okay. Right. So that is my magnetic field in terms of expressions. So in terms of value, it is also quite easy to find out the magnetic field because I know what is my V value. Okay. Directly, you can put here the V and R in terms of value. So if you write in terms of value, so in terms of value calculation also, it is quite easy to find out here. Mu naught by 4 pi E V by R squares. So I can take it here mu naught by 4 pi E. Velocity is 2 into 10 raised to the power 6 Z by N square. And what is my R term here? R term here is 0.51. Z square by N whole squares. This can be okay? V by R squares. Right? Now I know the value of the E. What is the E value? 1.6, 10 raised to the power minus 19. I know the value of this mu naught by 4 pi. Right? So you can solve it here easily. Great questions. What if the angular frequency is given as RPM? Convert the RPM into radian per second. RPM is anything a very strange concept. RPM. What is RPM? What is RPM? Rotation per minute. RPM means rotation per minute. rotation per minute. So one rotation is 2 pi and 1 minute is 60 seconds. To convert into SI unit, RPM is not a concept, it is just a unit conversion. So I hope you understand here the simple approach is there. Okay? If you want to remember the formula, you can remember the formula. I don't suggest to remember the formula. Just suggest you that remember the proportionality sign for the R and V. Okay. So with that little ideas, you can find out any problems, right? Okay. So I hope you understand here this approach, how to deal with this chapters, how to solve these problems. The only major issue with this chapter is there is a lot of calculation involved here. Okay, so calculations will be avoided. You need to slightly think in the proportionality sense. Okay, slightly get tricky. You can avoid this most of the calculations. We can take here some problems from the previous IIT. What is the IIT asked here? So very simple question IIT asked. Nothing much twisted problems are not this. Very basic questions are there. So if you have an idea what is the basic proportionality relation, you can solve maximum problems very easily. So see, here's one questions. Many question is there. As I told you, na, IIT, there's a lot of questions are there. See, is how easy this question IIT asks is. In the Bohr's models, the ratio of the kinetic energy, the total energy of the electron in the quantum state n. So simple. Question is yes. Yes, who will give me the answer? Ratio of the kinetic energy to the total energy. Yes, Aditya.
-1:1, sir.
-1:1 here. Yes, you're right. It is going to be a -1, but being a scalar quantity, we can say that. So in this chapter, in this hydrogen atoms, energy, kinetic energy, and potentials, they are exactly have a same relation as the gravitations. Okay, so the criteria is that it is equals to kinetic energy is negative of total energy and potential energy is double of total energy. So this relation, I suggest that you should have an idea. Remember it. Very easy one. So next question IIT asked here is, this is a somewhat here little twisted question is this. But it is not that much twisted. You have done this type of problems in your chemistry also. He said that energy of 24.6 electron volt is required to remove one of the electron from the neutral helium atom. The energy required to remove both the electron from the neutral helium atom is. So in chemistry, you call this 24.6 with a special name. Energy required to remove the first electrons. What is the name of that? It is called ionization energy. Again, it's a chemistry terms. Ionization energies. If you remove the first electron, not second electron, just first electron if you remove, that is called ionizations. For second electron, third electron, that is not called ionizations because it's already ionized. So from the chemistry, it is called ionization energy is theirs. Now for the first electron, he has already told you what is the energy required. And for second one, we can find out because helium has only 2 electrons, doesn't have many electrons, huh? Only 2 electrons are there. First to remove, this is going to be 24.6. Now what is the second? For second, I can apply Bohr's models. Now it's a single electrons, we can apply the Bohr's models. That's it. So how much energy it will take? to remove the electrons. So the energy of this electrons, if I'm going to be taking care about single electron, so the single electron in n equal to 1, z equal to 2. Helium has z equal to 2, right? So helium has z equal to 2 and the electron in the ground state only. So n equal to 1. So my energy is minus 13.6. Okay? Z square by n squares. Z square by n squares. So in your ground state, your energy is there, n equal to 1. This is my situation. Then n equal to 2, 3, 4, 5, and you want to remove. You want to remove means you want to go toward the infinity. So you want to make a jump from n equal to 1 to n equals to infinity. So final energy is going to be a 0. Initial energy is minus 13.6. Z value is 2. N value is 1. Okay, that is my initial energy. And what is the final energy? You want to take it here? Infinity. Infinity, final energy is 0. So how much energy you required? This is required here is a plus 13.6 into 4. And that is the energy required for second electron only. Okay? Not total electron here. This is for second electrons. For first electron, they have given. Why they have given? Because you can't apply the Bohr's model for the first electron. So they are given. So total he is asking. Total, I can say it's a 24.6 plus 13.6 into 4. That is my total energy required to remove both of the electrons. Okay. But what is the name of this total energy? In chemistry, you call this first electron is called ionization energy. But what is this total energy called in chemistry? Binding energy. That's called binding energy. That is the binding energy of atom. So that much energy is bounding the electron with the nucleus. Just as in gravitation we have discussed now, you are attached with the earth. So same way electron here is attached with the nucleus by attractions. So when the electron go to the infinity, so their energy becomes 0. So they become escape. Electron escape from the attraction of the nucleus, just like the rocket escape from the earth fields. So exactly like that. So that much energy is my escape energy. And this escape energy, second name is a binding energy. Energy required to escape. Okay? So total energy required to remove both of the electron from the nucleus becomes my binding energy of the systems. Right? I hope you understand the point, yes? So same question, they can ask you what is the binding energy of the systems. So answer here is ionization energy plus the energy required to remove the second electrons. Yes, Akash, what is your doubt?
Sir, but we got minus 13.6 into 4 now, sir.
So this is initial, na? Initial is minus 13, final 0. So what is required?
Okay, sir.
Of final minus initial is required, na? 0 minus.
Yes,
Okay.
sir.
So I told you, it's just a small questions are there. Just you have to be attentive to read the question here. In physics, we don't have anything extra. Simple only we are asking in the physics. Okay, already you have done in the chemistry. So as such in physics, we don't have much things. Hardly few problems are there which could be asked here separately. So I will discuss that tomorrow. Most of the questions are same as your chemistry concept. So that was consider a spectral line resulting from the transitions in the atoms and ions given below. Shortest wavelength is produced by. So shortest wavelength, it simply means here wavelength and energy both are inversely related. When you make a transition from N1 to N2, energy turn into my photon energy, and I can write this as a hc by lambda. Frequency is a c by lambda. So it is inversely related to the energy. Okay, right? So here only mod is important. You take the energy in such a way that frequency is coming out to be positive. So there is no question of negative sign here. So high energy minus low energy. Okay. So in this case, positive quantity you have to be considered. So who has a more energy change, that going to be have a less wavelength. Latest sum. First, we can discuss here this the basic sums, then we can twist it here. There is a basic or twisted one. There is no meaning of latest. No? So we have a lot of time up to Sunday. Okay, so many days are there for the same topic. Clearly, see. So in this case, what is my energy and wavelength? Inversely related. So there is no inverse relations. So it is already we have seen beta. Energy here it's related. What is my energy related is? Energy related here is a 13.6 z square by n squares. And this n term, if you want to see here the change, so this change is going to be giving me here this n terms. Transition term is same, 2 to 1, same for all. So this term is going to be the same. So it is only a matter of your z. More z, more energy, simply. Okay. So who has a more value of the z here? For hydrogen atoms, I'm going to be have a z value 1. Deuterium atoms, singly ionized helium atoms, lithium atoms. So I know hydrogen z is 1, helium z is 2, lithium z is 3. Okay. So clearly for lithium z is maximum, so energy is maximum for the lithium. Right? So for my lithium, Z value is going to be more. So energy is going to be maximum for our lithium. So lithium is the best answer here. So this change is proportional to my Z. So lambda is inversely proportional to your Z. So lithium. In same question, I twist it slightly. So lithium is more than helium, helium is more than hydrogens. If we want to compare deuterium and hydrogen, can we compare? Deuterium and hydrogen compare. Can we compare deuterium and hydrogen? Can we compare here deuteriums and hydrogens? Are they the same or different? For deuterium also your Z equal to 1, and for hydrogen also your Z is equal to 1. So if we think first view, so in the first attempts, the answer seems to be same, but it is not actually. If you try to compare your deuterium with the hydrogens, they're not same. There is a difference is there in the wavelengths. Okay, why the difference coming? So here you need to be understand. You need to be understand here. This formula 13.6 z square by n squares. They are for our basic atoms, which are not going to be your isotopes. So deuterium is the isotope of hydrogen. I'm sure you have an idea here. No? So what is the difference in the hydrogen and deuteriums? Hydrogen has one protons in the nucleus. One proton is there in the nucleus and one electron revolve around it. But in deuteriums, you have a proton plus one neutron is also there. So that is a slightly difference there in the nucleus. Okay. As long as if I'm going to be considered about the nucleus stationary, there is no difference in them. If nucleus is going to be stationary, both are going to be have a same wavelength. But if I assume that nucleus is movable, so there is a motion in the nucleus also, then answer is going to be different. Then answer is going to be a change. So how the things are going to be changed, we can just really see it again with our proportionality. Energy is half mv squares, okay? Minus half mv squares. If I go with the exact formula, so what is the exact formula for my velocity is proportional to z by n. Velocity is proportional to z by n. Proportionality, I can take it here as z, it could be replaced here as a kz e squares, and here is the nh cross into v squares. That is my formula. But this is the formula for stationary nucleus. For nucleus at rest. If nucleus has motions, then you have to be remove the mass with the reduced mass. Again, I hope you understand the point here. Reduced mass. Reduced mass is nucleus mass, electron mass divided by nucleus plus electron mass. So that is going to be the thing you need to be considered here. We can prove it also. I will prove it. But for the time being, you can just remember this way. If nucleus has motions, so just like our solar systems, so nucleus revolve around the center of mass and the electron also revolve around the center of mass. So almost results are same. Just you have to replace the mass of the electron with the reduced mass. And reduced mass term is mm divided by m plus n. Now if you go to our basic formula here, so my formula is depending upon the mass also along with the z. Okay, so it is depending upon the mass also along with the z. So deuterium and hydrogens, they have same value of the z, but they don't have a same reduced mass. So my energy is depending upon my reduced mass, and reduced mass depends upon the mass of the nucleus, right? So it is depending upon the reduced mass, and who have a more reduced mass? I can write the reduced mass this way. Okay, if you have a more heavy nucleus is there, this 1 by mass term is going to be less. So 1 by mu term is going to be less. So mu term will be more. So for heavy nucleus, your reduced mass is more, energy is more. Means the reduced mass of our deuterium is greater than the reduced mass of hydrogens. So all the energy of the deuteriums are greater than the energy of my hydrogen atoms. Correct, Beta? So I hope you understand here the effect of the nucleus. We can prove it, but without proof, just for the time being, you can consider the nucleus has motions, and simply you can replace the mass of the electron with the reduced mass. So energy along with the Z factors, N remains same, Z remains same for hydrogen and deuteriums. Only electron mass is same. But these formulas are for the approximation if nucleus is at rest. If nucleus is motions, So electron mass is not important. What is important here is a reduced mass is important. And reduced mass depends upon the electron and the nucleus, both the masses. So my energy is not actually depends upon the electrons. Energy depends upon the reduced mass. So I hope so. Now you can tell me what happened to my lambda. So lambda is inversely proportional to the energy, right? So you're going to have a deuterium wavelength is going to be less than our hydrogen. So just listen here. What I'm saying here is, sorry. So once again, listen here. What is happened in the questions? This question was quite simple. IIT asked a simple question. I have twisted the question slightly. Again, in IIT, they are asking only which of the following A, B, C, D will give the shortest wavelength. For shortest wavelength, I need highest energy. Okay, so wavelength is inversely proportional to your energy. So I can say here my shortest wavelength means inversely proportional to my energy. So less energy, high wavelength, high energy, less wavelength is required. Now energy depends upon my Z, so I can say it is inversely proportional to your Z. So hydrogen has Z1, deuterium has Z1, helium has Z2, lithium has Z3, right? So lithium has the highest Z value, so shortest wavelength is for lithium. Clear? Now my question is that in hydrogen and deuterium, if we compare hydrogen and deuterium, Z value the same. So do they have a same wavelength? So answer depends upon the approximations. If I take that nucleus is at rest, so energy only depends upon the Z value, and deuterium and hydrogen has the same Z value, so it is same. But if I consider the nucleus has motions, if nucleus is going to have motions, nucleus also revolve around the center of mass, electron also revolve around the center of mass. Okay? So everywhere the electron mass will be replaced by the reduced mass. You can replace the electron mass with the reduced mass. So energy now is not depending upon the electron mass. Energy now depending upon my reduced mass. So exact formula for the energy, if I write, it will be minus half mu v squares. It will be half mu k z e squares by nh cross. That is my energy if the nucleus has a motions. If the nucleus has motions. So for deuterium and hydrogen, Z value same, but mu is different. So energy is depending upon here my mu for our isotopes. If you have isotopes, my energy depends upon the value of my mu, right? Energy depends upon the value of mu. So I can say my wavelength is inversely proportional to the mu for isotopes. So for same Z value, okay, for same transitions, same Z, isotopes are differ, nucleus differ. So my lambda is going to be differ. Who has a more reduced mass? So deuterium has a more mass compared to hydrogens. So its reduced mass is also more. So deuterium has a more reduced mass compared to hydrogen. So that means it's going to have a less wavelength compared to hydrogens. So I hope is it okay? So if we arrange, so lowest energy is for deuterium, then hydrogens, then helium, and then lithiums. That is the order of lambda. Okay, I hope you understand the point, yes? 14th one first we can do, then we can come to the question number 5. So try here 14th one. ये तो हो गया ना? So we have already done. The minimum energy required to remove an electron from the ground state of a doubly ionized lithium. The बहुत easy है, very easy. Minimum energy required to remove the electron from the ground state of a doubly ionized lithium. This is a quite easy problem. Try to give me the answer quickly. For hydrogen, how much energy required for hydrogen? In ground state, you're going to have energy that is 13.6. Where you want to take? You want to take it to the infinity. That is the meaning of removing. So n equal to 1 to n equal to infinity jump is required. So in the ground state, you have 13.6 for hydrogens. And for lithium, that will become here my Z squares. Okay, 9 times. Finally, it is 0. Infinity, it is 0. So initial energy to final energy, that's it. Right? So that is the energy required to remove it. So energy required to remove here is, it is also called here binding energy. You can also call it here as a binding energy. Okay, so 0 plus 13.6 into Z squares, binding energy. In terms of electron volt. Yes, Satvik. Hello, Satvik. So answer here is 13.6 into Z square. Z is 3. You can calculate here for Z3, right? So question number 5 is quite different. And this is basically not related to your physics also. This is required here, chemistry concepts. But as this topic is quite common with your chemistry and physics, so maybe IT has asked this. So if element with the principal quantum number n greater than 4 were not allowed in the nature, so number of possible elements would be. So frankly speaking, I also have no answer for that. You can tell me from this chemistry point of view, quantum numbers. We can get it here. He's asking here number of possible elements. So what do you mean by element? What is, or how my elements differ? So element is differ by difference in their Z value. So each element has a Z value difference, right? So Z value is going to be here differ. What else they have different? Only Z value is different. Right? Okay, so in this case, he is asking here principal quantum numbers. What is my principal quantum numbers is going to be means here. So it's beyond your Bohr's model, and it is related to your, in chemistry, there is some principle is theirs to fill the electrons, shells. You are filling the shells, no? N equal to 1. For n equal to 1, for stability, you have 2 electrons are theirs. Okay. The valency is going to be 2. For n equal to 2, you have 8 electron valency is theirs, right? N equal to 3. N equal to 3 कितना था? I think it's going to be that formula I forget here. So that was in chemistry you have this Aufbau principle, I think so, right? So in the first shell we have 2 electrons, then 8 further, and n equal to 4. How much? I think it is that I exactly don't remember. So yes, tell me Uday. Hello Uday.
N equal to 18. N equal to 318.
N equal to 3, 18. N equal to 4.
18 plus 14.
18 plus 14. 32.
32.
Okay. So here means in equilibrium, in neutral atoms. In my neutral atoms, you have electrons and protons are same. So if you have n equal to 1, I'm going to have 2 electron, and for neutrality, you require 2 protons, z equal to 2. And this is going to give me a z equal to 8, n equal to 2. So this n equal to 2 including 2 or excluding the 2? It is excluding 2. So z value will be your 10. Then for n equal to 3, your total number of electron is going to be here my 2 plus 8 plus 18. Okay, 28. And for neutrality, my z will be 28. And for n equal to 4, I can say total number is going to be something here, 20 and 60. So z value is going to be here 60. Z value is 60. So the maximum numbers of z possible with n equal to 4 is my 60. You're right. That is the formula here. No? Number of electrons in a shell is 2n raised to the power 2. Same. Okay, anyway, we have to find out the number of elements. The number of elements means number of z. Here I am assuming that this is my electron formula. That is my electron shells. And according to the electrons, you have protons balancing it. So z value is going to be the balance of electrons. So z should be your 60. Yes, the best answer here is your D. So I hope so everyone get this idea here, right? Now this is the question IIT asked here slightly different because it required the concept of chemistry, not physics. How the electron fill the shell. This is not in the physics, right? But it is there in your chemistry. It is the part of syllabus. So IIT can expect that if this type of twist they can also make up. So this question number 25 first we can go, and then 24 we can go here. Electron in the hydrogen atom make a transition from excited state to the ground state. Which of the following statement is true? So he's asking here kinetic energy, potential energy, total energy relations. And relation is quite simple one. This is your, you did not understand the last question. So why you're asking so late? So what is my kinetic energy? It's a minus of total energy. Potential energy is twice of my energy. So he said that you are making a transition from excited state to the ground state. So in this process, what happened to my total energy, is it increasing or decreasing? Total energy in excited state, ground state, if you think as a magnitude, making a jump downward, so magnitude of the energy is increasing, magnitude wise. Okay, it is 13.6, and as n increases, magnitude is decreasing, but it's a negative term. Remember that it is energy is negative. Only magnitude here is increasing. So I can say that magnitude wise, your kinetic energy. Okay. So magnitude of your total energy is the same as the magnitude of kinetic energy. They are same exactly here. Same. So my kinetic energy is increasing clearly because okay, overall magnitude wise both are equals. So kinetic energy is going to be increased. And it's very common sense is this. If you are near the nucleus, you have more force. And for the more force, you required more velocity to balance the force. So speed should be more. Because it's very logical. If you're near the nucleus, you should have a more speed to balance the electrical attractions. That's why kinetic energy increases and speed is more near the nucleus. Okay. Or if you further, if you're going to be, remember this is over Z by N. So as you go away, your speed is decreasing, inversely relations. So near the nucleus, you have more speed. So I hope you understand logically also why speed more required. But what about the potential energy? The potential energy is going to be strong if your attraction is going to be strong. But attraction gives negative potential energy. Repulsion gives positive potential energy. So near the nucleus, there is a strong attraction. So potential energy is going to be strong, but with a negative sign. Okay. So magnitude of the potential energy is increasing, but overall potential energy, because negative sign, attraction gives negative sign, it is decreasing. So it is negative. That's why potential energy here is decreasing. Now you can give the answer for this question. So a simple question is, its kinetic energy is increasing and its potential energy and total energy decreases. So this is correct. Or A option is correct. Its kinetic energy decreases, wrong. Kinetic energy, total energy decreases, wrong. Kinetic and potential energy decreasing, all decreasing, no. So best answer is your A. Kinetic energy increases. So more near the nucleus you are, you have to be run fastly to balance the attractions. Yes, Sunat.
Sir, once can you explain the potential energy part?
Potential energy, see Vida, more attraction means more potential energy. Okay, attraction, you're going to be increase the potential energy, but in a negative sense. Attraction gives negative potential energy, repulsion gives positive potential energy. So U is a negative for attractions. So if you have a stronger attractions, it will become more and more negative. So near the nucleus, you have stronger and stronger attraction, it will become more and more negative. Okay? So
Sir, but
because
we
of
are
negative
taking magnitude. No?
Magnitude is increasing, but it's negative sign, so potential energy is decreasing only.
Okay.
It is not a vector quantity, it is a scalar quantity. Energy is a scalar quantity. Negative means less than 0.
Yes, sir.
Okay, negative means less than 0. In a vector, you can compare magnitude only, but it's a scalar quantity. You have to compare sign also. So in scalar quantity, magnitude comparison is not sufficient. Yes, Aditya.
Sir, if n decreases, kinetic energy will increase, no, sir?
Kinetic energy increases. Yes.
Option 4 we will get, sir. Means
Kinetic energy
all
increases.
All will increase, no, sir?
No, all is not increasing. All is not increasing. All is not increasing. See here, Take the sign into consideration also. What is your, okay, first understand from this way. If you are moving near the nucleus, so you require more speed because more attraction is there, right? Speed increases near the nucleus or not? Speed increases near the nucleus because you have a more force near the nucleus. We have this simple relation is there, na? mv square by r. So speed increases, and we have this relation also here is inversely proportional to the r. So if you understand logically, speed is near the nucleus more. Okay. If you're going to have a less speed near the nucleus, so nucleus will collapse you. So you have to be run faster near the nucleus. So speed is required more. So my kinetic energy is going to be more, right? Speed increases as n decreases. So kinetic energy increases as n decreases. Now what about the potential? So my potential formula is minus k minus k q1 q2 by r. So it is inversely proportional to r. R decreases. This term is increasing, but with a negative sign. Okay, negative sign is also there. Na? If my R is decreasing, so your potential energy is also decreasing. Na? Okay, and reason, logical reason is simple. Near the nucleus, you have strong attractions. Attraction decrease the potential energy. Okay, it will take the potential energy more and more negative. Stronger you have attraction, your energy is going to be decreases. Potential energy decreases more and more. So near the nucleus, you have a more negative potential energy. Okay? More negative potential energy is there near the nucleus. Right? And about your total energy. So total energy we can see here mathematically. So formula of the total energy is minus of K. So kinetic energy is increasing near the nucleus. So total energy is negative of K. So it is decreasing. If kinetic energy is increasing, your total energy is going to be decreasing. Right? So I hope it's looking clear. The last question. What is the doubt in the last question? So once again, here see the last questions. In this last question, it's related to your chemistry, not physics. For n equal to 1, you have 2 electrons. N equal to 2, you have 8 electrons in the atoms. Okay. N equal to 3, you have 18 electrons. N equal to 4, you have 32 electrons in a neutral atoms. That is the condition for your neutral atoms. So he said that if maximum number of the n is 4, maximum numbers, then what is my elements are possible. So different elements I need here means maximum z basically. So for n equal to 1, you have 2 electrons, so z value should be 2. N equal to 2, you have 8 electrons. So total number of electrons in n equal to 2 is 2 plus 8, 10. So z value is 10 maximum. With n equal to 3, we have maximum number of electrons is 2 plus 8 plus 18. So z value is going to be 28. For n equal to 4, this is the maximum number of electrons here, 60. So z value is a 60. So I need here z is 60. Okay. So elements are 60. Maximum possible elements are 60. So next question we can consider here is 24. Now here, read the question carefully. He say, imagine. So he's making a imaginary atoms made up of proton and a hypothetical particle of double the mass of electron, but having the same charge as the electrons. So he's asking here the longest wavelength of the photon that will be emitted has a wavelength in lambda and constant क्या पूछा गया इसने? Anyway, so what he asked here is the longest wavelength that photon will be emitted has a wavelength lambda in terms of Rydberg constant he is asking. And here R is for the hydrogen atoms. Remember, R here is for the hydrogen atoms. So what is the formula for the R with the hydrogen atoms and with this hypothetical atoms? So in this hypothetical atom and the hydrogen atoms, what is the difference? Instead of electron, you have replaced another particle which has double mass of electrons, right? So mass terms only you have to be replaced with the 2m. Figure it out? Mass term you have to replace. So let's you can do it exactly also, no need. Just think from the proportionality sign point of view. Velocity is proportional to z by n. It is independent of mass. So my velocity does not depend upon the mass. So there is no impact of changing the electrons. If you change the electrons, speed is not going to be changed. But yes, energy will change or not. So energy is my half mv square. So energy get doubles, right? Energy get here my doubles. So if we're going to be use here this new models, and if you're going to be compare with my hydrogens, so there is a factor of 2. Because mass of the electron is going to be doubles. Velocity is not changing with the mass, only half mv squares. This m term is going to be changing. So I can say in the new model, energy is double than hydrogen atoms, right? But what about my lambda? How we got here the lambda? So we got here simply the lambda from this relations. Energy changes are converted here into my hc by lambda. Okay, energy changes are proportional to hc by lambda, and this was written. You can also write it here this way. I can write here energy changes by hc 1 by lambda as a Rydberg constant into transition terms. Right? So he's asking for maximum longest wavelength he's asking here. Okay? So longest wavelength. So how much transition is required for longest wavelength? Longest wavelength need here, basically longest wavelength is here as my shortest energy. Longest wavelength that will be emitted. So longest comes from n equal to 1 to n equal to 2. So my transition terms will be your something 3 by 4. Okay? So here 3 by 4 factor is theirs. Now you compare the same thing here. Okay? Just compare here the same thing. If we compare with the new model and hydrogen model, so everything is going to be here my same. But I'm getting this factor, the energy of the new model is double than my hydrogen models. So this R for the new model is also going to be double than, because ultimately they are equal, no? Okay, so my R is depending upon my this energy terms. Energy depends upon the mass, so R is also depending upon the mass only, no? Okay, so this R factor is depending upon our mass. R is depending upon the mass. So I can say this Rydberg constant for my new models is twice the Rydberg constant of my hydrogen models. If you want to write down here the lambda, so it will be this wavelength is equals to my new model he's taking. And transition is there from 1 to 2. Transition term is there from 2 to 1 or 1 to 2. So in terms of my hydrogens, so hydrogen he given R. R is the symbol for hydrogen, the Rydberg constant he has given. So you can say it's going to be 2 times 1 minus 1 by 4 R. So it's 3 by 4 into 2. So you got the wavelengths, okay? The basic idea wavelength we can get here is that 2 by 3R. Okay, 2 by 3R. Or in the case of my hydrogens, 1 by R is your 91.2 nanometers. Why transition is from 1 to 2? He asked you the maximum wavelength. So maximum wavelength you require energy minimum. Na? So minimum energy comes if you make a transitions between N1 and N2. If you make further higher jump, energy is increasing. So lambda is maximum for these transitions. Right, beta? So yeah, no need to be just go exactly, just by proportionality, you can get the idea. Oh, sorry. My mistake is this. He is making a jump. All possible transition. Okay, sorry. All possible transitions. Just a minute. Here's all possible transitions to the first excited level. Consider all possible transition of this hypothetical particle to the first excited levels. So first excited level he is taking. So these are just my mistake here, slightly. First excited state he is asking. So he's not making a jump to the ground state. You're right. N value is not going to be 2 to 1. So normally we go to the ground state now, but he's not taking it to the ground state. So he is taking to the first excited state. So first excited state is N equal to 2. So you're making a jump to only N equal to 2. So for N equal to 2, I'm getting here the lambda maximum, and this lambda is a maximum for the transition from 3 to 2. Okay? So transition term is there from 3 to 2. So 3 to 2. Right? So I hope so understand this point here. Not confusing here. For lambda maximum, we are making a transition from 3 to 2. And the new R value is double of my hydrogen 1. So you take 1 by 4 minus 1 by 9. So it will be 5 by 36. Right? Good, I hope you understand the point here. So a lot of questions are there which could be easily understand or easily can be approached by taking the help of proportionality. In fact, maximum. You need not to remember the exact formulas. You can derive the exact formula also very easily. This is question number here 29. So in question number 29, this is also a very simple common idea basis. This doesn't require here any deep concept here. Very basic one is this. We say that transition from n equal to 4 to n equal to 3 is in the ultraviolet radiations. So for infrared radiations, what should be the transitions? We know one thing, that ultraviolet has a more energy compared to the infrared. Yes, ultraviolet here means wavelength lower than your violet, ultraviolet. So it's beyond the violet zones. Infrared, it's going to be beyond the red zones. So who has a more wavelength, red or violet? Red has a more wavelength. So energy is less for the red. So infrared has a less energy compared to my ultraviolet. So I want to check the less energy. Okay. We want to check here less energy. So n equal to 1 is there, 2 is there, 3 is there, 4 is there, 5 is there. So he say this is my energy. Okay. 3 to 4 is it's going to be ultraviolet. So which one will give me here the infrared out of the 4 possible options, right? Out of this one. So it's not asking exactly, it's just asking comparisons. Yes, Aditya. Yes, who will give me the answer quickly? Uday.
D.
I'm not getting your point. D. D, you're right. D is going to give me here the answers. Correct. It's going to be the D.
The difference between our will decrease.
So this diagram of the energy difference, it is not a uniform. So more better if I draw. So you have maximum gap near the ground state. So this gap is decreasing as you go higher and higher. So energy states are coming here closer and closer. So they become here closer and closer. So gap is keep on decreasing. So we can say that here the difference in the energy is decreasing as my n is increasing. So clearly from n equal to 3. So this energy difference here is, if I consider this 1, 2, so this 1, 2 has a more energy. So it is more ultraviolet. So 1, 2 is a higher energy compared to my ultraviolet. 3, 2. So 3, 2 also has a more energy compared to the ultraviolet. So wavelength is not going to be larger. 4, 2 is also going to have more energy compared to my ultraviolet. Only this 5, 4 has an energy less compared to my energy difference of 5, 4 is less than the energy difference of our 4, 3. So this may be a possibility. Okay? 5, 4 may be the possibility is there. No guarantee, but possibility is there. Okay, this is question number 36. Here, question number 36. Electric potential between the proton and the electron is given. But that's a hypothetical situation once again. Okay, not a real situation. Completely hypothetical situation is given. Yes, potential is hypothetically given in this way. So he say that apply the Bohr's models and get the relations between the R and the N. So all the concept we have derived as a standard hydrogen, they are not applicable here. Okay, so if I say that R is proportional to N squared by Z, this is not applicable. This is only for hydrogen atoms. Okay, in hydrogen atoms, we have this formula KQ by R. Potential formula is KQ by R. Right? Q is our minus KZE by R. So if my potential is just like a point particle minus KE by R, then this is applicable. But here, potential is something different. So I have to derive the result. How we derive here is very simple one. We have applied just two equations. One is I have to balance the centrifugal force. Centrifugal force is provided by the attractions. And the second one is our quantization principles. Only two equations we have used. No third equation we have used. First, I need here this potential is given. So what is the force value? Potential here is the potential. So potential energy we can write is going to be a EV. That is going to give me a minus EV naught log R by R naught. If I differentiate the potential energy, negative of that gives me the force value. The force value will be here minus EV naught. I differentiate the log differentiation gives me here R by R naught, okay, into 1 by R naught. Overall, R naught is going to be cancelled out. And I'm getting here as a minus EV naught by R. That is my potential energy. What about the force? Force value is minus du by dr. Minus du by dr is give me a plus EV naught by R. Okay? That is my force value. It seems to give me a kind of contradictions. Minus sign contradiction is giving us. So let me do here with exact sign. Okay, we can go here with an exact sign. Let me do it here with the exact sign. So the sign is contradicting. The potential is log V naught log R by R naught. We can write it here as a log R minus log R naught. This R naught term is a constant terms. If we go here exactly, first we can find out the field created by these potentials. So field is minus dV by dr. dV by dr, so it will be a minus of V naught log value is 1 by R. So my electric field is coming out to be negative, right? Electric field is coming out to be a negative. That is something strange. Why is strange? Understand here why it is strange. Strange in the sense that the direction of your electric fields is in the direction of your minus R cap. So R cap is going to be in the inward directions, right? If I take here the force on these electrons, electron being a negative, it will experience the force in the outward directions. Okay, so it can't make a stable nucleus. It will make my nucleus unstable. So I hope so. There is a misprint. There is a misprint. R should be in the bottom and R naught should be above. If I take R naught above and R in the denominators, then you can have a stable nucleus. Okay, so this is a little misprint is this. So correction kalana, okay? So try to do here little corrections. I'm just taking R naught above and R below. Reason, because this is making the potential unstable. Okay, so there may be sometimes in the books printing they do the mistakes. IIT is not asking this. This mistake is not the IIT. Only book mistake is there. So my electric field is now coming out to be a positives. So electric field is coming out to be now positive. Forces comes out to be in the negative directions. Okay, we can put here this force in the inward directions. So electrical field is outward and force is going to be here in my inward directions. Now, as you are moving, it can provide you the centrifugal force, right? It's possible here. So we can say here electrical force is equals to my mv square by r, and force value is a minus EE. E value we had derived, it's a potential by r, and mv square by r. Oh, r is cancelling. We want R only, and R is cancelling here. No problem. We can get here, sorry, magnitude we are only comparing. Magnitude is in comparisons. So they let us know here, if you're going to write here my velocity. So what is my velocity? Velocity will be under root of E by M V naught. That is my speed. Next thing he say that apply angular momentum conservation. So angular momentum is MVR and quantize it. So I'm getting here velocity, you can substitute there, that will give R as a function of your, V is constant. Here V is coming out to be constant, independent of your R's. So that means V is constant, M is constant, so my R is proportional to N here. So direct relation is there between the velocity R and the N. Strange thing is, because it's a hypothetical, okay? So it is possible to be as strange. So my velocity is constant, it is not quantized. This velocity is coming here independent of your N. Independent of the N. Here means if you are near the nucleus or you are away from the nucleus, in every situation, your speed is coming out to be constant. If my velocity is independent, your kinetic energy is also coming out to be constants. Kinetic energy is also coming out to be a constant. Okay, question is not about our kinetic energy and the speed. Question is about our R and N independence. So R is increasing here with the N. So in this hypothetical situation, it's possible. I hope so. You can understand it's a hypothetical. In real life, this is not possible. In real picture, this is not possible. This is related to your nucleus. This is also a very interesting question is yours. This is a very nice question, and if you understand here the quantums idea, you can give the answer here for these questions. Otherwise, it is going to create a lot of confusions. And the confusion is generally, I think so, is created because of the chemistry. In chemistry, when we say about the excitation, so they take many atoms. They don't take a single atom. So chemistry mostly they talk about multiple atoms, not about a single atom. And this question is about a single atom. So if you try to give the answer from the chemistry point of view, it may contradict your perceptions. So think it from the Bohr's point of view. Okay? Single atoms. What is given is, he said that a photon, single photon collide with the stationary hydrogen atom in the ground state inelastically. Inelastically means it's a concept of mechanics. So what is the meaning of inelastically here? Elastic means you are not giving energy, and inelastic means you are losing the energy. So here photon collide inelastically. So photon is giving energy basically. Okay? So photon is giving energy. That's why it is colliding inelastically to the stationary hydrogen atoms. Yes, Aditya.
Collisions of excitation alpha particles will not complete.
Which one, beta?
Collisions of alpha particle will not start and
So what is the collision, beta? Collision क्या कह रहे हो? Hello. I'm not getting your doubt.
not start and alpha collision of alpha particle.
Collision of alpha particle. Which alpha particle? I'm not getting a point.
Syllabus, sir.
So alpha particle collision, this is not part of
Started.
syllabus. Where you are asking here is Bohr's model, is there part of syllabus? And alpha particle collision, you say radioactivity. Alpha decay we have in the syllabus. In the nucleus chapter, we discuss about the alpha decay. Rutherford experiment, you're saying alpha particle scattering.
Yes, sir.
Hello.
Yes, sir.
Okay, in Rutherford, yes.
Narayana book they given after that.
In Narayana material, they have given lots of things. So Narayana, they can give n number of things. Alpha particle scattering in the Rutherford experiments, alpha particle scattering is not the part of syllabus. Okay? Only Bohr's model is the part of syllabus. Okay. Alpha particle scattering is just a rough idea you should have what is the Rutherford experiment is there roughly. Okay. So it's a scattering is not the part of syllabus. Here, it's going to be given here a photon collide with the stationary hydrogen atom in the ground state inelastically. Energy of the colliding photon is given here 10.2. Okay, photon energy is given here. Next is the interesting point here is after a time interval of microsecond, another photon collide with the same hydrogen atom inelastically with the energy of 15. What will be observed by the detector? So one photon of energy and electron of this part, two photons of energy, two photons of this energy, and one photon of energy 10.2 and one photon of energy 1.4. So it's going to be a important point here. This important thing here is that okay. So in this case, here you need to pay attention that timing is given microsecond. Okay, that is important here, microseconds. So when you excite the atom, it just immediately go to de-excited stage. It excite, de-excite. How much time it will take to excite and de-excite? Nobody knows exactly, but time is 10 raised to the power minus 8 seconds. So it is going to be much smaller than compared to microseconds. The purpose of giving here microsecond is means atom excite and de-excite. So before you given the second atoms, your first atom is already excited and de-excited. So now you can understand this question here. We have hydrogen atom, electron is there in the ground state, right? So photon is coming, and this photon is going to be absorbed. And as a result of this absorption, what happens? My electron make a jump, and this jump is from which stage? 10.2 electron volt is theirs. Now, to do this type of problems, it is better to remember here some more information. It is helpful in the problems. Because every time if you do the calculations, it comes out to be very tough. But if you remember this few results, it will be easy. So for the hydrogen atoms, starting to 2-3 level, you should have an idea. You should remember that. So like n equal to 1. For n equal to 1, what is the energy? Minus 13.6. Minus 13.6 electron volt is the energy for n equal to 1. So you should remember that. For n equal to 2, it will be minus 13.6 divided by n squares. Okay. So minus 13.6 divided by n squares. So this comes out to be your nearly n squares divided by 4. Okay, so it's going to be a 13.6 divided by 4. So 3.4. So energy in this n equal to 2 is minus 3.4 electron volts. Then n equal to 3. How much energy is there n equal to 3? It is 13.6 divided by 9. And this is a minus 1.5. Exactly calculate करना. Up to second decimal place, how much is that coming here? 13.6. Just 1 minute. 13.6 divided by 9. So some value related to the hydrogens, okay? You can remember it. I just tell you what are the, not all values required to be remembered, but few is important to remember for fast calculations. 1.51, that is the energy. And this next one, n equal to 4, also you remember. Up to 1, 2, 3, 4. Up to 4 only, just remember this. So 13.6. 13.6 divided by 16. So getting 0.85. So these are the energy levels, that much you remember. That is for Z equal to 1. For Z equal to 2, they are getting square. All these levels are going to get here squares. For Z equal to 3, it is going to become here 9 times. So in between these energy levels, so few energy gap is also remember here. Between n equal to 1 and 2, how much is that gap? This gap is your 10.2. So energy gap between the first and second is 10.2. So next, this gap is also important to remember here is, this is 12.1. 12.1. Okay. So the meaning here in between these two, it's a 2.1. 2.1. So next gap here is, if you want to remember, it's not compulsory, but if you want to remember here, 13.6 minus 0.85. 12.75. Okay, many gaps are not required, just this 3 is enough. So if you remember these levels, it is going to be enough. So for hydrogen atoms, this 3, 4 energy, starting 3, 4 energy level, you remember for easy comparisons for rough idea. So like this questions, they have given 10.2. So 10.2 is exactly fit between your n equal to 1 and n equal to 2. So where my electron make a jump? Electron is going to make a jump from first excited state, ground to first excited state is going to make a jump. Now immediately it is going to be the de-excite. So de-excite, it is again going to emit here these photons immediately. Now second photon is coming. When the second photon is coming, already my electron is in the ground state. So electron is already in my ground state. The second photon is coming with the energy that is 15 electron volt. So it's a very high energy. Why it is going to be high energy? So simple reason is you have in the ground state your energy is minus 13.6. At infinity it is 0. If my electron absorb the 15s, so up to the infinity it need only 13.6. So where it will go? It will go beyond that. So it will escape from it. Okay. So energy required to just remove the electron is 13.6. And it is more than 13.6. So electron is not going to be returned back. It will escape. It is completely going to be a escape. And it is going to be escape with the kinetic energy 15 minus 13.6. 1.4 electron volts. Now, is that ever electron is going to de-excite? So second time, electron is not going to be de-excite. It is going to be escape and escape with energy 1.4. The real picture is quite complicated, but it is the simplest pictures. And questions syllabus is about the simplest picture only. Okay, never complicated here. Now see the option here. A photon of energy 10.2 and electron of energy 1.4. Yes, that is the final stage. So in the final state, you have already first photon excited and de-excited. So you have one photon of 10.2. And second time electron is going to be ionized. So it is going to be give me kinetic energy of 1.4. So best option is your A. 2 photon. 2 photons? No. 2 photons of energy 10.2? No. 1 photon of energy and another photon of energy 1.4? No. You don't have a second photon. Electron is coming out with energy 1.4. So it is not emitting this photons. Right? In a real life situations, electron escape is not that simple. So, but we are taking here no other effect. Only one nucleus effect is there. If I consider only one nucleus effect and forgetting about all other nucleus, then electron will comes out with the 1.4. See? So this 4 levels you remember 13.6, 3.4, 1.5, and 0.84. And this 3 energy differences that is going to be useful in problem solving. So the next here is 49 questions. Largest wavelength in the ultraviolet region of the hydrogen spectrum is 122 nanometer. The smallest wavelength in the infrared region of the hydrogen spectrum is ultraviolet and infrared. How we know about that? It's ultraviolet or infrared. Actually, here related to this question, also you need have some point to be remembered. Some data you need to be remember here. So there are 4-5 series are there. Lemon series there, Barber series is there, questions, fund and bracket series. So these 5 series, they have a different range. For example, if we consider here quickly, lemon series, where the lemon series start and where the lemon series end. So lemon series means if there is a jump to my ground state, that is going to be here my lemon series. So first is called alpha lines. The next line is called here beta lines. And the last one is going to be called here as a limit line. So that is the last limit. So first line is called alpha line. Okay? Lemon alpha lines. So if I want to find out here my lemon alpha lines, so it will be equals to, we're going to be have a Rydberg formula is 1 by lambda is equal to Rydberg constants. And transition term is this 1 by n1 square minus 1 by n2 squares. So for alpha line, what are the transitions? It is 2 to 1. Okay. So 1 by alpha line, that is the transition from 2 to 1. So that is my 3r by 4. And alpha line, we can say here 4 by 3r. 1 by r is 91.2 nanometers approximately. 92 approximately. You can think of it as a 92 approximately. So how much is that the wavelength for my alpha lines? It comes out to be something around 30 or 4, nearly around 120. 120 nanometer. That is the starting of my alpha line. The 120 nanometers. And ending last lines, which is a limit line here. If I go for the limit lines, so limit line, it is going to be have a transitions from infinity. So I can say the lambda limit line here is R. Okay. So lambda limit is 1 by R, and this is nearly around 92 or 91. Approximately 91 exact answer. You can check your books here. Nearly 92. So range of my lemon series, if I write the range here. So lemon series, what is the range here? It's a very small range is this. So you need not to remember it, but if you remember, so in some problems it is useful. So lemon line, if we write, lemon line minimum is nearly around 90 and the maximum is going to be here 120 nanometers. So is it in my visible spectrum or it is beyond the visible spectrums? Your visible spectrums is start from something around 350 nanometers. Blue color is 350 and red color